Welcome to my presentation called What Do I Do with 1,000 Codes? I know that the choice is really tough right now. I think there are at least 3 competing sessions around a similar performance related or big computer related subject. So what can you do? Luckily, everything is recorded. So if you need the slides, if you need the recording, this will be available online for free. So for your later interests. This is the summary of the talk. This is what I usually work with, well, for the past year. It's a lot of fun, but we'll get there. My name is Andrzej Grzesik. I have a Twitter. I have an email. If you need the slides faster, email me. I'll be more than happy to email the slide deck back to you. So if you need anything, email is the king. A few facts about me. I'm very proud to be a Java champion, a Java 1 rockstar for when Java 1 was still a thing. I'm involved in Polish Java user group. I'm one of the organizers of the conference. I have a tendency for very dry jokes, which you already know from the start. I was involved in Software Craftsmanship Krakow and Krakow Hadoop user group. I am from London, as in that's where I live. I'm originally from Krakow. I like going to conferences, and I work with hundreds of machines since 2010, give or take. And this is a special kind of fun, because if you have the opportunity to work with multiple machines at the same time, you learn to automate and you learn to distrust. And also it means that some of the machines, even though they look completely the same, some of them will misbehave. And surprisingly, it's something I started to enjoy, and I kept on doing big data /backend /distributed kind of stuff. I am working with a company called Simudyne, which does agent-based modeling. What they produce is an SDK, which means a set of libraries that you can use to implement your own agent-based modeling models, but I'm not representing them at this moment. All opinions are my own. If you have any questions, there are 2 ways to handle it. First, you can wave your hand, and if you wave your hand, if I notice, I'll try to pay you some attention. If not, it might be because of that light. It's shining directly into my eyes, so sorry. And there is Slido, and I know that some people will be monitoring Slido and they will be trying to grab my attention if there is anything there interesting. Ask the questions as they appear, because we don't want the interesting thought to leave us. And we have to start with a motivating image. Yeah, some people started to smile, so that's exactly what I think. Also, if somebody was curious, this has nothing to do with Java agents whatsoever. So Java agents are not what I'm doing. I'm talking about agent-based modeling, which is similarly named, but it's not that thing. If you want to know about Java agents, I would say look up ByteBuddy and Raphael, who is an author of ByteBuddy, and that's probably what you are going to look for. Also, this talk is about my experience writing software that runs on big machines, which means it might not apply, and most probably does not apply to a Spring Boot running with a Docker container, using Hibernate and having some strange features. I don't use a database. I don't run websites. The software I do doesn't really have a massive UI, so it's mostly about simulating and simulation and using all the cores massively as much as we can and optimizing for wall clock time. This is what I care for, and this is more or less like a work report. Things I found, things I've learned, and things I still find confusing, and things that cause some of my hair to go slightly grayer. Also, a joke from yesterday. There is a saying attributed to the Chinese, at least by Terry Pratchett: may you live in interesting times. Some people say it's a blessing, some people say it's a curse. I would say it might be both, depends on how you want to interpret that. But if you look at computers, especially if you remember your first computer, well, first, there is so many people that don't really have the concept of having a first computer, because computers were always around them since they entered the market. For me, there was a thing when we got a first computer at home, and that was, wow. For me, that was a 386. And if you look at history, specifically look at this nice chart that somebody was kind enough to put on GitHub. Transistor counts still keep increasing, so Moore's law is happy. What you can also see is frequency kind of plateaued, which means we don't have 7 gigahertz computers running at home, sadly, unless somebody has a liquid nitrogen tank with infinite capacity, then will. Or if you're into crazy overclockers stuff. But typical power of a computer system is kind of also, it is not kind of, it has plateaued. And there is a good reason for this. If you have a data center, energy efficiency and heat dissipation is a serious problem. If you have 1,000 of CPUs, you need to dissipate heat of thousands of CPUs, and this becomes an important and complex and expensive thing to do. So what we get instead is the frequency has plateaued, the performance still slowly keeps going up, but the number of cores has started to go up rapidly. And this is visible in every single computing device that we have access to. If you have your phone probably might have 8 cores, maybe even more. This machine has 4 physical cores, which means after hyperthreading it's 8. Current MacBooks have 6 cores. You can buy processors, experimental ones, that have exactly 1,000 cores. Those will be ARM-based, and there is some complexity to do with that, but logically it's still a 1,000-core machine. And you can imagine that programming for 1,000 cores is a bit different to programming on a single or double or quad-core machine. Also, if somebody's paying attention to the chart, you can see that the single thread performance keeps increasing slightly. This is because of the optimization and new instructions that are being introduced in further generations of CPUs, so things like AVX 512. If your software is happy to use those, the performance of that piece of silicon will increase naturally. And as I say, this is a work report. What works in my specific case, might not apply to what you do. You have to use your best judgment. After all, you're engineers. You know what to do. You know what to do when, and you know what to do when not to do something. Let's look at supercomputers. So supercomputers, those massive, big, expensive things that take tens of millions of dollars to order, it takes usually at least a year for them to materialize when you want one. They are ranked. There is a ranking called the top 500, which lists, as the name implies, 500 most powerful supercomputers on the planet at a given moment in time. They do an update to it twice a year. And in June 2010, it was possible to get onto position 37, so very, very high, with a mere 1,280 cores. 1,000 cores is not a lot, but obviously it's not a competition, but it is. So you can see some lovely skyscrapers from Moscow's financial district. It's not a competition about which building is the highest, but it actually is, and people will do strange things like extending antennas and building extra floors just to go higher and higher and higher. Same goes with the supercomputers. Because of the cores that become available, you can now buy CPUs that have a lot of cores. Position number 1 from November 2018 had 2,400,000 cores. This is a lot. I don't expect it's a single piece of software that runs in there. It's probably used for some very complex simulations, and it's probably a lot of software that runs in there, but 2.5 million cores almost. That's a lot. That's complex. I cannot imagine writing anything that would run efficiently on 2.5 million cores. However, we can then look at Amazon. Amazon, and I took this screenshot not so far ago, has those special machines that have 448 logical processors, which means before hyperthreading it's half of that. and they have 12 terabytes of RAM and Those are very specialized machines. They are the to support running SAP HANA, most probably. SAP HANA is an in-memory database that likes RAM, and to process a lot of data that sits in memory, you need a lot of cores naturally. Can you run Java in such an instance? Yes. Can you get it easily? Well, you'll have to contact support because that's very specific hardware that they would have to procure and make available for you. So you probably can't just put in your credit card and have access to this instance. At least my account didn't show it as available. And then we can look at Azure, which goes even further, which has, with a machine that has 20 Xeon E7-8890 V4 CPUs, 20 terabytes of RAM, and that translates to 480 CPU cores, which means 960 after hyperthreading. So we're almost at 1,000. If your reaction is like that, that was my reaction. Of course, if you want to access that, you have to, again, talk to Microsoft, ask them to, ask if there is one available already or if they can build one for you. This will require some business commitments and some serious conversations because building such a machine is not trivial. If you look up those CPUs on Intel's Arc, the recommended prices times 20 plus all the RAM, this amounts to a serious amount of dollars. However, those things become available. And then Microsoft blogged. If you can see it, I congratulate you. If not, they did say 10792 cores, which is a special build of a machine for testing the Windows kernel, which has almost 900 physical cores, because logical processor, so V cores, is 1792. That means that Windows can do it. It's an experimental and an engineering sample of their kernel, but it's possible. The fact that it's possible means it opens new possibilities. The question then becomes, okay, I have such an amazing piece of hardware. What can I do? What should you do? What makes financial sense, of course? Well, to you, it probably depends, well, as it depends to me. If you want to compare existing clouds, more reasonable machines, somebody was kind enough to make a comparison, and according to that comparison, the link is in the bottom right. And as I said, if you want slides, email me, I'll be more than happy to share. Oracle Cloud is quite high in price to dollar. So one option for you is, of course, use the cloud to get access to a lot of CPUs. However, that comes at a price. Because if you want to use a cloud, and I don't want to say cloud vendor A because there are at least 2 vendors that start their name with an A, and that's a very bad letter choice. Let's consider workload. I will not tell you which vendor that was. I will not tell you what workload that was because that's not really that important. What is more important is the time is normalized to the shortest observed runtime, and you can see that 30% almost of all the runs were very similar, around 1.0 in the duration. However, there is this bump, and this bump says that 50% of workloads were longer than 1.3 of the shortest observed runtime. Is it a problem? Well, it really depends on the software that you're building. If you care about supporting a lot of users, probably not, because 1.3, if your request service time is fast, remains fast. If you're doing something that's time critical, it might be a bit of a problem. And clouds, sadly, do exhibit this behavior. Why? Because if you're using hypervisors and you can have a noisy neighbor, they might be doing stuff that's not nice to the VM that you're running in. Another point of measure, 15 out of 100 were more than twice the shortest, and the longest observed was something around 6.5, if I remember correctly. Another workload, this is the chart I got. Does it mean that you should not use the cloud? I don't know. most probably using the cloud for running a production system is a great choice. Most probably it's going to save you a lot of time and nerves and procurement and hardware and confusion around having a data center, and is actually hard work. However, if you are writing software, and I repeat, I'm writing software that does simulations and cares about the wall clock time, this chart means to me that I need to do my optimization work in an isolated, controlled environment. That also means that I might need to try to get some strange hardware sometimes to be able to experiment on that without having to risk any of the cloud pollution that you might get. And somebody could observe that, yeah, but I could also get bare metal instances on most of the cloud providers, and I would say, yeah, that's correct. Those should not have those problems, but the usual machines that you get can have problems like that. Why do I not talk about averages there? And I want to look at it as latency charts. This is the answer. There is a great talk by Gil Tene. Thanks, Tomer, which is called How Not to Measure Latency. It's available in so many places on the internet. If you have never seen it, I would recommend you do. And then coming to what I do on a more on a daily basis. The problem that we're trying to solve is agent-based modeling. Agent-based modeling, also Matrix is 20 years in this year, time flies. Agent-based modeling is a class of computational model. So you model a single entity, let's say a participant in the traffic, a participant in the market. You instantiate it 20 million times or however many times you need, and you simulate as in run the interactions. There is a question, awesome. So, okay, let's do it this way. Which JDK version and vendor would be the most suitable to run on 1,000+ cores? Where is the person that asked this? Okay, I can't see you. So it's a complex question. Which JDK? I usually use JDK 1.8, but there is a caveat. The question is, do you want to run a single one? And the question, there is some question about network and GC and so on and so on and so on. And we'll get there, or grab me after the talk for more detailed discussion. Coming back to agent-based modeling. So agents, in short, interacting with agents, which translates to software as a lot of objects sending messages to other objects. And there is an environment which you could look at a specialized piece of object. As programmers, if you've ever attended a code retreat, not code retweet, you might be familiar with Game of Life. Anybody knows it? Anybody has coded one? Yeah, it's a trivial, simple, great for developer experience and debugability and nothing really much else model, which could look like that, which means on every tick, so the artificial measure of passing of time of a simulation, every cell looks at how many cells around it are alive. If that's 2 or 3, it means that this cell will stay alive. If not, it dies. And you repeat as long as you want for a billion cells or how many you want. What that means under the hood is communication pattern is going to look something like that. A moment for the photographers. So agents, let's say agent number 1 sends a message to agent number 2. Agent number 1 sends a message to agent number 3, 4, and so on and so on and so on. So you have a lot of messages emitted. Communication pattern might be even, or it might be more centric like that. And this is just a picture. And which one is more popular? It all depends on the model that you're using. And if you're curious about different approaches, there is a list of agent-based modeling software and the implementation. There is a lot of open source, there is a lot of software that does it actually, and the reason is because the whole technique was invented or described by von Neumann in 1940, so it's nothing really new. But the question would be then, who uses ABMs? Well, finance industry, uses that quite a lot. You could look at humans as agents in the economy. You could model traffic with agent-based models. You could do environmental simulations with animals as agents. You could identify individual particles in an environment as agents and let them interact. You could do the same for stellar bodies. It's your choice. Some known industries and some known organizations, Bank of England is very well known to use ABMs for a lot of things. They were kind enough to actually make papers and publish them. So they have simulated the British mortgage market using ABMs. That means that you could simulate the mortgage market, so buying and selling houses with the resolution of an individual entity. So you can see if Mr. John Smith or Mr. Krzysztof Brzęczyszczykiewicz Jan Kowalski wants to sell a house, or if you increase the inflation rate, what happens? How many people will start buying houses? What will happen to the price indexes? Why do I say you can see what will happen? Because you will run this simulation, which simulates the entire UK environment, and you will run it a lot of times with a lot of parameters differed, and you will see what happens. And that will generate a lot of data, and that can be useful. Why? Because you can see what happens. You can detect shocks, you can detect things that have never happened, but might be a very lucky or unlucky coincidence of facts. And then somebody could say, why do I even do it in Java? Especially after slides like that. All I will say is, I personally deeply disagree with some of the texts present on this slide. I do believe in enterprise environments, Java is a hugely popular platform, and if the organizations I consider, for them it's easier to find Java proficient people and let them work with a Java-based framework. And if you look at the total time from problem definition to having a solution that works, Java offers very good, I don't want to say performance, but time to, let's call it time to market. Finding proficient Python people, I don't know, I don't work with Python. If somebody knows, you can make your own comments. C++, it's a great language. However, developer productivity, as in getting the solution that does what it's expected to, for me is easier to achieve in Java or JVM-based languages. Okay, that thing aside, I've mentioned the cores, I've mentioned the hardware. The premise of the startup I'm part of is that because of that, it's a great time to build ABMs. Why? Because it's possible to compute them in a reasonable amount of time. And then a joke while I drink. So, I said I'm building ABMs. My requirement is optimizing for wall clock time. The scenario is I run 1,000 simulations. If each of them will take, let's say, 10 minutes, which is a good default. If you have, let's say, 640 cores, this will mean that you will have to wait for around 47 hours to get the results of your simulation. Which means if you can shorten a simulation by a minute, you win a lot. And that translates to dollars very easily. And there are some challenges. And I will show you some charts and some numbers which represent something, but do not draw any conclusions because I've made it very, I want to make it very clear. This is not about micro benchmarking. This is about what different things that you might observe when running with strange hardware. Let's have a look at the concurrent counter. What are the methods that you know that you can use to make a concurrent counter? One, of course, the first thing that you know, that you learn as a Java developer is using synchronized. Easy, works very well, is very well documented. It might be considered slow by some. Some people might say, no, you have to use atomic long. Some people might say, no, you should use long adder because it's going to be faster if you have many cores. And then somebody is even smarter and they will run a benchmark. And this is a benchmark that wants to illustrate just one thing. Top line is being run on a MacBook. Bottom is being run on a server-grade CPU. what you can see easily by the position of shapes and colors is that MacBook A looks faster, and B has the order of different results completely twisted. What happened? Well, there are two things. First, there is an amazing presentation by Alexei Shipylev about problems running micro benchmarks, as in how hardware can cheat you. But basically what I get in here is there is a thing called NUMA, which is non-uniform memory architecture, but what that translates is if you have a multi-CPU system, some of the memory will belong to one CPU, some of the memory will belong to the other CPU. So if you have a workstation that looks like that, and that's just a random picture from the internet, part of the memory and the physical chip will form node 1, and the second one will form node 2, and then you're happy. There is a tool called NUMA CTL under Linux operating systems that will be able to tell you which RAM and what's the capacity, what's possible. And knowing that you're happy, you have two options now. You can write NUMA-friendly code, or you can avoid NUMA whatsoever. And here I can come back to the question which JDK version I would recommend using for such problems. Well, if there is that problem, you could try to tackle it slightly differently. What I sometimes do is NUMA CTL bind processes, so you make a process run only on the RAM and only on the CPU that doesn't cross any boundaries, and then you communicate over localhost, because localhost on a Linux box will usually be quite fast and have reasonably low latency. So the times are interesting, but then times are even more interesting because recently, as in 2 years ago, AMD made a huge comeback. Who here has a Threadripper? Who here is excited about Threadrippers? Yeah, some hands. This is what a Threadripper 2950X looks like from an architecture point of view. There are two dies. They have two compute units. Each of the dies are connected to a memory controller directly, and they are connected with an, I forgot the name, InfiniBand? Infinity Fabric, yeah. And that's fine. Great CPU, works as a workstation CPU very well, but then there is the bigger version, bigger brother, called 2990WX, which has 4 dies, 8 compute units, but there is something missing here. You might notice that immediately, you might not notice that. It's half of the dies don't have direct access to memory. So you have non-uniform memory architecture within one physical CPU, because it's like multiple CPUs glued together already. And then let's have a micro benchmark. Again, it's not important what was being run, but what I wanted to show you is the results that you get between a server processor that has all the dies connected to memory controller versus a very fast or slightly overclocked Threadripper might look like that. The noteworthy thing, again, the order is flipped. What is also not visible at all is the Threadripper runs faster by default, because Epic has to be able to run 24/7. A Threadripper might be overclocked. It might be a workstation that your data scientists use with a lot of GPUs at the same time, and you just manage to run this benchmark there. And then come dual socket epics, so dual socket AMD enterprise CPUs. Are you using them right now? Most probably not. Will you be using them in the future? I don't know, but they are becoming more and more popular. You can buy them from a lot of vendors, and they seem to offer a better price to availability or performance for workloads like, let's have a Spring Boot based web app. You don't need the fastest possible single core. And then you can say, yeah, but that's a niche, and why would anybody glue CPUs together? But then, recent announcement, beginning of April this year, Intel announced that they want to do a 2-socket CPU, which is combined out of 4 dies, 2 of them stacked together. And then you try to benchmark that and compare it all, and the numbers might show something completely different. And let's go even further. this is comparing a Threadripper 2990WX and an E7 V3, so a very expensive Intel CPU, and you can see that for this particular benchmark, the Intel CPU has basically killed the Threadripper without, let's call it mercilessly. So if you feel confused, please regain your calm by looking at this HTOP picture. Also, if you don't know this, HTOP is a tool that shows you usage of each core. It will show you red when there is system load, and it will show you green if it's user load. However, the way it does it, it scans the file system every minute, every second, and this will be updated every second. So it can be called disturbing, but it makes for nice pictures. But the times are interesting, and if you want to understand everything what happens, I definitely still have much to learn about distributed systems. But let's start at the basic, because this is Leslie Lamport. He is the author of this quote: "Distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable." However, the problem is now with up to 1,000 cores within a single computer, the question is, what makes a single computer? Is it a single process running on a single thread on a single core? Is that a single NUMA node? There are different levels of abstraction. There are different levels what makes a computer. And then we can look at time. If you have a computer or a bunch of computers asking each other what's the time, well, the answers might be slightly different. That's known, and that's great. And somebody could say, but you can use NTP. NTP is the Network Time Protocol. It's a very good protocol which reduces a lot of the errors. However, somebody might be still completely asleep. And then you get to learn that time is not guaranteed to be monotonic across different cores in a Linux. I will let that to sink in. So if you have multiple CPU system, the time, as in if you do system.getTime or something similar, time presented or the value returned across different cores might be different. Not monotonic, which means something that was wall clock later might be shown as wall clock earlier, which no comments to this slide apart from that. But there is a solution to that. Luckily, distributed systems is something that has been tremendously researched over the past years. This is a very important, very good paper by Leslie Lamport about vector clocks, or one that starts discussing ordering events and coins the term vector clocks. If you have never read it, if you've never read it, I would recommend you do. In short, what you want to do is introduce time as an explicit context, explicit concept in your system, and treat time as something that you manage yourself. Don't rely on the operating system too much, because you might get something that's not super consistent. If you do care, that might be a problem, which means if you're running a simulation, don't rely on external time, run time within the simulation yourself. And then let's take a step back. We have multiple machines, or we have machines, and we have racks. At the top of the rack is the top of the rack switch, as the name suggests. That's not the Tor that you can see, is not the Tor with the hammer, sadly. And those things usually have something interesting. Something interesting might be presented as SFP inserts. Basically, what I'm trying to say is their network cards will be different to what you have in your, let's have a look at the MacBook. And you might observe something called TCP incast, where TCP fails completely because of Windows and how it works. But I will not explain that, because that's easy for me now to point to somebody. There is Tomer right here, who will on Friday at 13 have a presentation about TCP IP. So if you want to know what TCP incast is, maybe he will explain that. We'll see, or you'll see. But I will mention serialization, Because we all live in a happy world in which serialization is something that's given to us as Java the platform, or if you're building web applications, you can consider internet that is eternally running in debug mode, as in it's text-based. It's great if you're still serving over HTTP1. Let's consider something simple, like a game of life with a population of around the UK. Let's say every agent wants to send to everyone a message. Let's make it simple. Every agent sends one message only. The message will be 1 kilobyte. This will produce around 76 gigabytes of traffic. Is that significant? Is that not significant? I don't know. But what is important to know is over 1 gigabit connection, this will take around 10 minutes to transfer. Which means you might get into a funny situation in which you're benchmarking something on a single machine or using your home network, and your network chart or traffic chart might look something like that. And is there anything wrong in there? Not directly. However, you might notice that this is limiting around or cutting off around 100 megabytes. The problem is, in a data center, this is not representative of what network connections the machines that you're running with will most probably have. Right now, it's 10 gigabit is a standard. It's very common to find 25 gig or 100 gig machines, especially if you work with the bigger ones. Which means if you notice that CPU is having absolutely no problems or you want to optimize something, the external factors, the ones that you are not able to replicate, might affect the overall performance of the entire solution that you're working on. And then what works? Because I've said a lot of things that can go wrong. First, approaching the problem in a serial manner. Luckily, with messages, it's easy because you have a huge queue, and queues have been researched in computing for a lot of years. If you've read about buffers and ring buffers, if you read about the disruptor from LMAX, these are all using serial processing. Why are GPUs fast? Why are FPGAs fast? Because if you can vectorize the data input and if you can use a huge insert into a very fast processing entity, you will get fast performance as an end-to-end. What that means to me as a software engineer is some of the system I implement will try to use event sourcing. Event sourcing is not a silver bullet, and I think there is a question. Okay. Can time be fully controlled if we have the GC? I am afraid if you have an artificial sense of time, GC is completely orthogonal to the problem. If you are relying on the operating system, even if GC does not activate itself, different elements within the system might get a different answer. If you're running on multiple physical CPUs, it's something different might be present. Rust explicitly states that in their docs, other languages do the same. Some people try to make workarounds, and they do succeed most of the time. GC, sadly or not sadly, does not guarantee us too much, and it can confuse people even more because you might pick up the time, start doing something, GC might kick in, and then something might happen later. So it depends. I would say it's a good question to talk in person after, because I want to finish with the slides first. So event sourcing, what it means? Events. That means that instead of calling methods, I emit events. And if I emit events, that means I can reorder, I can rearrange them, I can reason about them. And that gives me the power of being able to control what's happening, how it's executed, and I can optimize depending on the hardware. If I'm running an agent-based system, that means I can rearrange agents, I can change things, because a method call is very hard to cut away in half and then resume elsewhere. If I have an event signaling or asking somebody to execute something, I can hold that event and I can accumulate all of them and I can deliver them to a specific place later when it fits me. Some conclusions, or what did I conclude so far? Getting the basics right which means Corman and the Algorithms book, it goes a very, 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 very long way. Keeping it simple helps a lot. And there is something called the morning paper. If you're a subscriber, it's awesome. If not, I would recommend subscribing to the morning paper. It's a newsletter that on a daily basis, while the author is producing them, delivers a computer science paper summarized and explained to your mailbox, so you can read something while you're traveling on the tube, in a bus, on a train, well, wherever. It's a great source of information, because if you're working in a domain like that is affected by what's happening in the hardware, you will learn a lot of interesting things. Algorithms, obviously, any algorithm book is something that I just keep using all the time. It's surprising at how useful divide and conquer as the paradigm is. And if you need an approach, cut your problem into smaller pieces, divide and simplify, and keep doing that until you can't anymore. If you want to lock, the best way is not to lock, which means lock-free algorithms, which goes back into computer science papers again. If you need a solution for tomorrow, if you are working with multi-CPU machines, buy one for yourself. You can get it off eBay for reasonably cheap. I think £1,300 is around, it's cheaper than a MacBook. If you're using a MacBook, it's a great typewriter, it's a great development machine, but it's not representative of what's the target environment. And if you care about how the target environment affects your runtime, I would say you should have a machine like that you can experiment with. You will learn a lot. Please, please, please define your criteria and analyze the problem as a whole. And at last, because somebody most probably will ask about micro benchmarks, at first, just guess, don't measure anything, but make a guess, and then make a hypothesis, or the guess, verify what happened, and distrust the results, which means if you think that something happened in a particular way because of something, try to make a completely reverse change and see if the problem reacts to what you're doing the way you expect it, and you will be surprised. Or at least I am. This is so important that it's even mentioned in any JMH test that you run. They say that the numbers below are just data. To gain reusable insights, you need to follow up why the numbers are the way they are. Use profilers, design factorial experiments, and so on and so on and so on. And I did say profilers, and somebody might say, yeah, if I have a performance problem, I will just use JProfiler or Visual VM or anything of that kind. And then there is another recommendation from me. Profilers are distrustworthy entities by Nitzan Vakart. Amazing talk, amazing writer. If you follow his blog, you're happy. If you're not following his blog, start following his blog. And also, if you want to learn a lot, also look at the assembly that your Java code is producing. I would recommend a tool called vtune. It's available for free since recently, and that's quite awesome. If you need priority support, if you want to submit code samples and want them to remain confidential to Intel, of course, you're always welcome to buy a license, but the free version works very nicely. However, I use it on a Linux box. If I am on a Mac, it gives me a UI that can analyze the results, but it will not be able to execute tests on the MacBook. Just mentioning Windows, I have no idea because I don't use Windows. And I'll finish with last thing. If you're working with large volumes of data, reactive, the approach, the fundamentals is your friend. Look at the reactive manifesto. Try to approach problems in a way promoted there, because that goes a long way. Externalizing concepts of back pressure, making your system aware of what's happening, not just waiting for everything to happen, works fine. And we'll finish with this. Anybody recognizes the quote? Okay, that's one of the ancient philosophers used to finish every speech of his with, and at last I think that Carthage should be destroyed. A ponadto uważam, że Kartagina powinna zostać zniszczona. So I can say thank you. If you have any questions, come over. If you want to follow up the discussion from the questions I've seen, come over as well. I'd be more than happy. Thank you for your attention. Enjoy the rest of GeeCON.